next video is probably going to be the longest one. So again, feel free to fast forward, rewind, skip around. It's not a big deal. What you want to do though is you want to make sure that you have the basic concepts. So we're utilizing all of the equations that we just talked about from above. The first thing that's going to feel very uncomfortable is writing the expressions for these redox reactions. Redox reactions, as you're probably aware, have a tendency to have coefficients that are a little bit all over the place. And yes, you do need to sort of join information together. So the first thing you want to notice is, again, we're doing a thermodynamic expression. That means that anything that is in aqueous solution needs to be molarity. So our manganese ion, for example, will be in brackets to represent molarities, and it'll still be squared, so watch those coefficients. Our liquids are still going to be left out, but our chlorine, notice, is a gas. That means we're measuring a pressure in atmospheres. Since we're measuring a pressure in atmospheres, that doesn't mean that you're going to forget about the 5 as the exponent. In the denominator, you've got permanganate ions, and again, because it is a solution, that'll be molarity. We're going to square that one. Here's where it's a little upsetting, because you've got hydrogen ions, and in those hydrogen ions, you're going to raise it to the power of 16. At the same time, you've got chloride ions, and for those, you're going to raise those to the power of 10. That's where a lot of people feel uncomfortable, because thus far, the equilibrium expressions we've created have had rather small coefficients. But with redox reactions, you got to be a little bit more flexible with that. This unit is also meant to go through and help you by putting together all of the different units. So keep in mind, at this point, you now have information about solving partial pressures from the gas laws. You have information about getting a hydrogen concentration from acid-base and using a pH. So there's a lot of areas now from which Mr. Seiler and I can pull to end up filling in some of these equations. Be flexible about thinking about that. Start really using that to your advantage. Question 2. We're now looking at the EMF, which again is the voltage of a particular cell, and we're going to calculate the maximum work from a gram of aluminum. So some things to keep in mind as we look above. We've got a voltage, and since we have a voltage, we can solve for the maximum work with this equation. So let's go ahead and look at that. Oops, sorry about, ooh, I don't know how to fix that. Ooh, and my phone is buzzing. Sorry about that. Oh dear, hold on, pause. All right, we've got a delta G equals negative N Faraday voltage. All right, so first thing, we've got our voltage. That's going to go very nicely into E. We've got our Faraday's constant. That is, again, on your green sheet, so that'll go very nicely since it's just a value, which if you look above is just 96,485. And now we do need to figure out the N value. So as we look at our N, notice that you can do it one of two ways. Aluminum is switching to aluminum ions. So a 0 times 2 aluminums is turning into a positive 3 times 2 aluminum ions. That means we're changing by 6. No, you don't like that way? All right. Then go to copper. There are 3 ions of copper. Each is a +2. That's a 6. And 3 copper solids, each is a 0. So again, we're going to change by 6. Those are your 2 ways. Pick which one you like. All right, so now we fill in. We've got a negative 6 times Faraday's constant times voltage. All right, as you plug that in now, right, you're going to get your answer. Now the problem with this answer is very simply that it's with respect to the reaction as the reaction is taking place. So according to this reaction, you have 2 moles of aluminum reacting and 3 moles of copper reacting. We happen to be looking at 2 moles of aluminum. So this is the number of joules per 2 moles of aluminum. But the question is not asking us for joules per 2 moles, nor is it asking us for joules per gram, joules per 1 mole. It's actually asking for joules per gram. So for every 1 mole of aluminum, you're going to find the molar mass of that aluminum, which I believe is there. I totally made that up, which I'm not supposed to do. Hold on. Yeah, that's good. And then you're going to go ahead and calculate. So take your joules from delta G, divide by 2, then divide by the molar mass, and now your final answer should be that delta G will be 5,000, roughly 400 joules per gram, or 5.4, a negative value of kilojoules per gram. Your choice. All right, question number 3. We now have a fuel cell that is a voltaic cell, and again, every fuel, every battery is voltaic because it's spontaneous and therefore giving us electricity. This particular fuel cell has been employed by NASA on spacecrafts, and again, basically the gist is using some very simple things that are very light in weight. So we're going to go ahead and calculate the standard EMF using those 2 reactions. And then separately, we're going to calculate the standard free energy for this reaction. Okay? As you take a look then, in order to create this reaction, some things that we want to do. We want to definitely flip the first reaction so that the 2 waters that are each a liquid are over on the product side. That means we're going to have our hydrogen gas with our hydroxides reacting to form 2 liquid waters, as well as releasing off 2 electrons. That's going to make our voltage positive 0.83 rather than the negative 0.83. We also want to make sure that our oxygens are, let me see here. Flip it around. Oh yeah, we want our oxygens to be reactants. So let's put our O2 with our 2 waters. Ooh, how about them apples? Plus 4 electrons. So we're going to leave this reaction alone. Now, does anybody see why I'm going, oh? All right, if you're thinking in your head, it's because we need to cancel the electrons, and there's no way of doing so unless we multiply the first reaction by 2. You are right. So we are going to multiply 2, 4, 4, 4, don't change it. That's the difference between voltages and Hess's law, right? With enthalpies and entropies and Gibbs free energies. Okay, so let's go ahead and add those together. We now have 2 hydrogens. We're going to go ahead and delete all of the hydroxides. We're going to cancel all of the electrons, thank goodness. We're going to cancel 2 of the waters, boink, which will leave us with 2. We still have an oxygen. And now we're going to add together these 2 voltages for a positive 1.23 volts. All right, so that answers the first question. Calculate the standard EMF of the oxygen-hydrogen fuel cell, 1.23 volts. Part 2, calculate the standard free energy change for the net reaction. So the standard free energy change, if you remember, our choices are these reactions up here. Since again we've got a voltage, let's use this in order to calculate it. Whoops, let me slide up just a little bit more. So we're going to go ahead, we're going to take delta G. We need a negative NFE, which really means we're going to do a negative. How many electrons did we cancel? 4. So 4 electrons times the Faraday's constant times the voltage, 1.23. So clearly this reaction is spontaneous, and I know that because my voltage is positive, and as I run my calculation, I also know that because delta G for this reaction turns out to be negative. So it's 47,000 joules, and that's going to be 47,000 joules for 2 moles of water. All right, last question. How does it compare to delta GF, so the formation reaction? The formation reaction looks like 1 hydrogen plus 1/2 oxygen makes 1 H2O. So literally, right, the formation of a substance, that would be water, forming 1 mole of it from its elements, that would be hydrogen and oxygen, at their standard states. This Gibbs free energy of the reaction should be exactly half. And it should be half because as you look above, there were 2 moles of water. So for every 1 mole, which would be the Gibbs free energy, we would divide it by 2. Which answers the third and final question to number 3. All right, number 4. A voltaic cell consists of a half cell with iron dipping into an aqueous solution, and the other half is silver dipping into another aqueous solution. We're going to obtain the standard free energy change for the cell using standard free energies of formation. Good thing that they're listed. That way you don't have to pull out your data sheet. So the first thing that we're going to do is, again, write yourself a reaction that is complete. So because we've got iron and silver, in order to figure out what is occurring here for a nice balanced reaction, we need to start out by deciding who is going to oxidize and who is going to reduce. How do I know that? Because these two things we're being told is basically a spontaneous reaction. So if it's a spontaneous reaction, we need to be able to determine what's occurring. All right, so go to your standard reductions table. And again, we are looking for iron and iron 2 right there. And we're also looking for silver ions and silver. Perfect, right? Oops, right there. All right, so silver ions turning into silver is spontaneous with a positive 0.8, which means that iron will be turning into iron ions. So let's go back to our problem. And we're going to have silver turning into silver ions with a voltage of positive 0.8. And then we're going to have, wait, that can't be right. What did I just say? Hold on. Oh, silver ions turning into silver. Okay, hold on. Silver ions turning into silver is positive 0.8. Sorry about that. Which makes iron turning into iron ions negative as reduction, so positive as oxidation, 0.44. Let me just double check that number. Yes, perfect. So reversing that reaction, we now have a positive 0.44. All right, as we add the reactions together, Again, keep in mind our electrons need to cancel, so we're going to be doubling the silver ion reaction. Do not change anything about that voltage. So now we have 2 silver ions. We have an iron solid turning into iron ions and silver solid, giving us a total of 1.24 volts. All right, so we're going to obtain the standard free energy change for the cell. So delta G is going to be equal to the products, which will be iron ions, -85, minus the reactants. Remember that the silver is a solid and that's its natural state, so it does not have value for its Gibbs free energy. And also remember, iron solid is the same way, but we are going to have 2 ions of silver, so 2 times 77. All right, as we put that together then, we've got a -85 minus 2 times 77, so a total of -239. And again, remember folks, this is in kilojoules. All right, questions on that? Right, you can't answer me. Sorry, that was habit. Okay, let's go on to number 5. Calculate the equilibrium constant from the standard EMF. So again, we're going to go to our table and we're going to look at the values. So I see here that my iron and my iron ion are already in that order, which means they are the ones being oxidized. So remember that was this reaction here, but it's reversed, so we're going to have a positive 0.44 volts for that one. And then we have lead ions turning into lead solids, so we want to be looking for that one also. So lead ions, lead +2, there it is, turning into lead solid. So notice that that's negative, but it's the more positive of the 2 reactions, which is why that's the one that's going to be reduced. All right, so that's a -0.13. All right, so our standard cell potential will now be, oops, there we go, will now be a positive 0.31 volts. All right, in order to calculate the equilibrium constant, again, you want to be able to utilize the equations that were given earlier. So as you scan through your values, the easiest one is going to be this one right here. So it's going to be E cell equals the RT over NF times natural log of K. So again, it's E cell equals NF. Oh, no. RT over NF ln K. And let me just double check. Is there a negative sign? No, there is not. Perfect. So there we go. Now we're going to go ahead and fill that in. So keep in mind our voltage is 0.31. R will be 8.31. We're at 25 degrees Celsius, which we're given in the problem, so 298 in Kelvin. The number of electrons passed is a matter of looking at your lead turning into lead. So 2 electrons, or by all means look at iron turning into iron, so 2 electrons. So we've got a 2 right there. Your Faraday's constant. Why did I just totally forgot what Faraday's constant is? And my phone is ringing, so hold on. All right, so where were we? We were talking about this. So this should be, whoa, hello. Well, this should be 96485. And then natural log of K. And so by using this, this is going to give us the the K that we're expecting to see as the reaction takes place. And as we look at that, right, we're going to just do a simple calculation. All right, so now we have a lovely K value that is a 3.1 times 10 to the times 10 to the 10th, positive 10. So a nice positive value for the E cell showing the spontaneity, a nice large value for K, again showing the spontaneity, which is also known as the reaction tendency in the forward direction being very high. All right, question number 6. As we go through, right, what is the potential for this? We have a concentration that is not standard. And I know that because if it had been standard, it would have been the value of 1. So we're looking at a half reaction. And again, all of these equations can be used with respect to a half reaction, not just with respect to a redox reaction. So as we look at this, we've got 2 electrons. Sorry, those are really bad too. Taking the iron ion and turning it into iron solid. For this reaction, because we have this concentration, we want to be calculating with, in fact, the Nernst equation. So keep in mind the Nernst equation is twofold, right? We need to know the theoretical value for the cell, and we also need to write an expression for Q. As we do so, right, we're going to have E equals E, and instead of a cell, we're going to have just the gaining of electrons. So in this case, it's the reduction of it as a theoretical value. And then keep in mind, we're going to be subtracting RT over NF times the natural log of Q. And let's go ahead and fill in the expression for Q. Because it is a half reaction, we're going to have no product being present. That'll be a 1 for the solid. But we are going to have a concentration of the iron. And again, we want a concentration because iron is an aqueous solution. And we don't need to have gaseous reactants. So as we take a look at this then, we're going to go ahead and first utilize our reduction table. So find your reduction table. And again, with that reduction table, we're using the iron 2 with the iron. And since we're going in the reduction, we are in fact going with a negative 0.44. So this value is going to be a negative 0.44 because it is reduction. Our R value, 8.31. Our temperature, since we're not being told the temperature, let's assume that it is in fact a standard, so 298. The number of electrons passed, 2, as you can see from the balanced redox or reduction reaction. And then again, Faraday's constant, 96.485. Now we're going to take the natural log, and here is where we would plug in. So we were lucky that it was 1 over the concentration because it was a nice 1-to-1 ratio. So no exponents have to be present, but we do need to make sure that we plug in the value. At that point, it's a matter of calculating. And so if you haven't already been running these calculations, you really should just double check that you're doing everything correctly. As you go through, be sure that you're substituting in all of the values. So to help you out, this value, really, is that right? Oh no, that's totally not right. Hold on. All right, we're going to be taking 0.44 and subtracting 0.12, which will leave us with a voltage of 0.32. That will be the voltage of this particular half cell as it's run with a very low concentration. And that is also an excellent example of the Nernst equation. All right, we have one more example, that is number 7. And notice in number 7, we're doing a number of things. First off, we are using a pressure of a gas because now we have hydrogen as a gas. We're also using a pH value, so that is going to dictate what is occurring with our hydrogen ions. So we're looking for the cell potential when the hydrogen electrode is immersed in a sample of acid rain, and the acid rain happens to have a pH of 4. Since the acid rain has a pH of 4, as well as our aluminum having a 0.2 molarity, we are definitely not at a standard sort of condition. So again, we're going to be using E cell in this case. Again, we're going to set it equal to the E cell that we know is a standard, and then subtracting the RT over NF with the natural log of Q. And in this case, keep in mind, we want to look at what that Q, we're going to look at what that Q represents. So as we write the expression for Q, right, I'm going to go ahead and put it back into this equation. And that means that we will have the concentration of aluminum ions raised to the second, while we have the pressure of hydrogen gas raised to the third. And at the same time, there's no aluminum solid, but there is going to be a concentration of hydrogen ions, and they'll be raised to the 6th. Again, keep in mind that you now know information about acids and bases. So with a pH of 4, you know that the hydrogen ion is going to be 10 to the negative 4th. And again, it's not just going to be 10 to the negative 4th, it's going to be 10 to the negative 4th raised to the 6th power. As you look at this then, we can go ahead and do some information with E naught. So let's go back to our reduction table. And as we look at our reduction table, we will remember that the hydrogen ion is the reference cell, so it's a 0. But down at the bottom, we have our aluminum reaction. As reduction, it's a negative 1.66. So as we look at our reaction, we are not using aluminum as reduction. We're actually using it as oxidation. So we're going to take a positive 1.66 with our reference cell, which is 0, and come out with an E naught of positive 1.66. So as we start to fill in this equation, right, we'll be solving for the cell. We'll be using our standard potential, which we just went through. Our R value, 8.31. As you notice, we are at 25 degrees, so 298. As you look, again, you're looking to see how many electrons. How many is that? 6, that's right, 6 electrons. Faraday's constant, 96485. And then filling in the natural log of Q, you have a crazy value of 0.2 that you are going to square, a pressure of 1.2 that you are going to cube, and a value of 10 to the negative 4th that you are going to raise to the 6th power. I know that feels weird. Do it anyways because that is the thermodynamic equilibrium constant. All right, as you sit down and do the calculation, again, it's going to be rather hefty because there are quite a few things going on here. All right, calculate. There we go. All right, you are going to be taking a positive 1.66, and if all has gone well, subtracting 0.22. So you'll end with a 1.44 volts of this particular reaction at equilibrium. All right. Let's say instead that you decided to put the electrode into a sample of shampoo. So now this means that if you have a 1.17 volts, you have a voltage, not a theoretical voltage, but a voltage of 1.17. And now we're going to solve for the pH. So again, folks, it's 1.17 is now going to be equal to 1.66. You're still working with all of the information for R and T and N and F for Faraday's constant. And now in the midst of your natural log, you are going to be taking and solving for the value of hydrogen ions. And again, remember, it's not just hydrogen, it's hydrogen to the 6th power. So work through that calculation. All right, if your math is going well, you have now gotten to 1.2 approximately times 10 to the negative 51st is equal to your x raised to the 6th, which means that your x value, which is also your hydrogen ion concentration, is going to be 3.3 raised to the negative 9th. And now using what you know about natural logs, logarithms, and pH, you are going to go ahead and solve for that. And the pH turns out to be a lovely 8.48 as your final answer for the concentration of hydrogen ions being represented by pH of the shampoo solution. All right, ladies and gents, those are some excellent examples. There are some additional ones, of course, in your textbook. Hopefully you're doing those online practice problems.